Hey, welcome to The Explainer. Today, we're diving into a really key topic for your GCSE chemistry exam, energy changes in chemical reactions. This is all about section 4.5.1 of the AQA spec, so yeah, let's get right into it. So let's start with something you've probably actually used. Think about a freezing cold day and you crack open a hand warmer, or maybe you've twisted one of those instant cold packs for a sports injury. It's not magic, right? It's just perfect, everyday chemistry in action. And by the end of this, you'll know exactly what's going on inside them. We're going to break this down into four main chunks. First up, we'll get the core definitions sorted. Then we'll look at how to visualize these changes with reaction profiles. After that, we'll tackle bond energy calculations, which is for the higher tier. And we'll finish up with a handy exam checklist. So let's start with the absolute basics. Honestly, the names give you the biggest clue you're going to get. Just think exo for exit. Heat energy exits the reaction. It gets transferred to the surroundings. And when we say surroundings, we mean everything else. The beaker, the air, your hands. That's why things feel hot. On the flip side, think endo for enter. The reaction has to pull energy in from the surroundings to happen, which makes the surroundings get colder. That direction of energy flow, that's the whole game. You see exothermic reactions literally all the time. Combustion is the big one. Burning anything gives off heat and light. Duh. Another absolute classic is neutralization. You've probably done this in class. When you mix an acid and an alkali, you can literally feel the beaker get warmer. That's an exothermic reaction. And that right there is the secret behind our hand warmer. Inside that little pouch, there's a chemical reaction going on, usually the oxidation of iron. It's designed specifically to be exothermic, to give out heat and keep your hands warm. It's just controlled chemistry. Endothermic reactions, well, they're a little less obvious in day-to-day life, but they're just as important. Thermal decomposition is a key example. You have to constantly put heat in to break something down. And a really cool one to try in the lab is mixing citric acid and sodium hydrogen carbonate. You can feel the beaker get super cold. That's because the reaction is literally sucking in energy from its surroundings to keep going. And there we have it, the answer to our other mystery. When you snap one of those sports injury packs, you're mixing chemicals, usually ammonium nitrate and water. This kicks off a super fast endothermic reaction. It just sucks in all that heat from the area, making the pack, and hopefully your injury, get really cold really fast. Okay, so we've got the definitions down. Now let's see how we can actually visualize these energy changes using something called a reaction profile. Think of these diagrams as a little story, showing the energy journey of a reaction from start to finish. Right, before we draw anything, you have to know this term, activation energy. It's the absolute minimum bit of energy needed to get a reaction started. Imagine you've got to give a boulder a big shove to get it over a hump before it can roll down the other side. That shove, that's your activation energy. Every single reaction needs it, doesn't matter if it's exo or endo. Okay, let's build one for an exothermic reaction. First, you draw your axes. Then, you mark the energy level where your reactants start. Now, because this reaction releases energy, we know for a fact the products are going to end up at a lower energy level. So you draw a line for them down below. Then, you just connect the two with a curve that goes up over that activation energy hump and then all the way down to the products. And this is what you end up with. You can see the reactants started with more energy than the products finished with. That difference is the overall energy that got released. See how the reaction goes downhill from start to finish? That's the classic look, the visual signature of an exothermic reaction. Now for an endothermic profile. We do pretty much the same thing, but with one massive difference. Because this reaction takes energy in from the surroundings, the products are going to finish at a higher energy level than where the reactant started. That's the only real change you need to remember. So your final diagram looks like this. The reaction goes uphill overall. The overall energy change is positive. Energy has been taken in, absorbed from the surroundings. If you can draw and label these two diagrams correctly, trust me, you're grabbing some easy, guaranteed marks in your exam. Okay, quick heads up, this next bit is for all you higher tier students. If you're studying foundation, you don't strictly need to know this for your exam, but hey, it's still pretty interesting stuff. The key to all of these calculations boils down to two simple rules. Rule 1, you need to put energy in to break chemical bonds. That's an endothermic process. Rule 2, energy is released when you make new bonds. That's an exothermic process. Any chemical reaction is just a balance between these two things happening.
So to work out the overall energy change, it's just a bit of simple accounting. The exam will give you all the numbers you need, the bond energies. So step 1, add up the energy for all the bonds you have to break in the reactants. That's your energy in. Step 2, add up the energy you get back when you form all the new bonds in the products. That's your energy out. And the overall change, it's simply energy in minus energy out.
So what does your final answer actually mean? It's simple. If your final number is negative, it means more energy was released making bonds than you spent breaking them. So the reaction is exothermic. If your number is positive, it means you had to put more energy in to break the old bonds than you got out making the new ones. That means the reaction is endothermic. Okay, let's pull all of this together. We've put together a checklist based directly on what the AQA specification says you need to know. Use this to double-check you've got everything covered. Just take a quick look at this list. Can you explain the difference between exo and endo just by what happens to the temperature? Check. Can you talk about why hand warmers work? Check. Can you draw and label both types of reaction profiles with all the key bits? Check. And for you higher tier folks, can you do the bond energy calculation? If you can nod your head and say yes to all of those, then you are in a brilliant position for this topic in the exam.
And let's finish on this question. Now that you actually get the science, how could you use it? What kind of reactions would you need to find to create a better self-heating can of soup or an instant cooling drink that stays cold for longer? This is where the chemistry you learn in a classroom becomes the key to designing the cool new stuff of the future.